Hi friends, this is Shubham Kantrai from Railtel and I have been working as a manager technical in this project from past 2.5 years. So I want to give you some insights regarding the project and want to spread education how this will benefit the Indian Railways in terms of operational voice and dispatcher. So let's move forward. So here are the list of the content. So the overview of HSMCC, and then there will be introduction to LTE. Then we'll move forward to how LTE fares better than the GSMR, and then multiple railway services over LTE, advantages, modernization project scope, bandwidth and SLS requirements. So how we have planned for SLS throughput requirements and what's the bandwidth requirements for ATCS and MCPT. And then we have network connectivity architecture depicting the connectivity of each and every component to the data center and the connectivity of data center components to the onboard units and all that. Then we have all LTE component description. Each and every component will be described in brief. MCPT, how it will benefit, what's the location based addressing and functional based addressing and this architecture. Then dispatcher, section controller, station master responsibilities and all that. Frequency level redundancy plan. So how frequency level redundancy can be achieved, how we have planned for 10 and 5 megahertz of spectrum, impact for Indian Railways, and the use cases. So let's move forward. So HMCC, it will improve the rail operations, safety, line capacity, market share, and efficiency, thereby enhancing customer experience. So sorry, so if this particular technology is implemented, it will not improve the safety and security of the passengers, but it will improve the line capacity and hence market share and efficiency of the train operations will be increased. There will be day-to-day railway operations which will get benefit from this particular technology. So the standards that we are strictly adhering to are FRMCS and 3GPP. FRMCS is Future Rail Mobile Communication Standard. Technology uses 4G or LTE. Features to be supported by LTE technology is train to ground, train to train in MCPT3, automatic train operations and ATCS level 2 traffic, passenger safety, in-cab signaling, location-based addressing, functional-based addressing, dispatcher solution. So we will take a look in detail in the coming slides. So HMCCC is a opportunity to consolidate and leapfrog. It will improve the passenger experience, critical communications. So critical communication is your operational voice, ATCS, and ATCS will improve the safety and security of the passengers. Emergency operations will be enhanced. The trackside monitoring, asset management, predictive maintenance, which comes under the IoT enabled services. So IoT services can also utilize the LTE technology, as NB-IoT, which is also known as narrowband IoT, is standardized in 2017 and LTE has a support for it. So LTE, if we deploy LTE based SMCCC, then IoT enabled devices can also be used in the railway environment. So passenger experience will also be increased by providing Wi-Fi on trains. So this is conditional if it's allowed or not. On-demand content, video surveillance, and if there is one more functionality called Wi-Fi offload. If a customer is traveling, Airtel customer is traveling in a train and does not have full network coverage, so that particular user can use our Wi-Fi services to get the full coverage. That is Wi-Fi offload. So if it's allowed, we can do that as well. What is LTE and long-term evolution? So LTE is first introduced in 3GPP release 8. Currently 3GPP release 13 is implemented commercially. So rolled out in India from 2014 and introduced mobile broadband capabilities for the first time. So if you remember, 4 or 5 years back, we used to have 3G technologies, but after the introduction of 4G technologies, we used to see the video content on YouTube in full HD without buffering. So the broadband capabilities it has given us, it's huge. So the technology that is behind the LTE is OFDM, which is OFDMA technology for downlink, and SCFDMA for uplink, single carrier frequency division multiple access, and orthogonal frequency division multiple access, which is both based on OFDM. and this has a support for FDD and TDD, frequency driven duplex, and time division duplex. So band 14, which is 700 megahertz, is the FDD band. So if you see over here in OFDMA, they are different subcarriers if you see, but in FCFDMA there is only one carrier. So this user over here is a single user. So from all these subcarriers, one of the subcarrier is being used by this from getting the information over here. Then this particular single carrier is being used to send the information again to node B. So why is that so? This is because to enhance the mobile broadband capabilities and to retain the battery capabilities. For example, your user equipment or handset is a very small device with a small battery. So enhancing the broadband capabilities will also drain its resources. So in order to reserve the resources, battery drain, this functionality, which is known as single carrier frequency division multiple access, is used. Now advanced antenna solutions, which is MIMO, beamforming, and flexible channel. MIMO is multiple input and multiple output. Beamforming, so multiple input and multiple output means transmit and receive. For example, if we have a network of 1 Mbps speed and we put 2x2 MIMO, that means our speed will get increased by 2 into 2 times, that is 2 Mbps. Beamforming is basically targeting a particular area. We can target a particular area using the beamforming technology in LTE. There is a flexible channel support. If you see 1.4 megahertz, 3 megahertz, 5, 10, 15, and 20. These are different chunks which can be used in LTE. No less than and more than these chunks can be used. So if I want to divide 10 megahertz, I can divide it in 5 and 5, 5, 3, 1.4, but not 5 megahertz cannot be divided into 2.5 or 2.5 because it's not defined in LTE. If you see the air interface multiple access techniques, over here, if you see, this is on the same plane, but these are orthogonal with the spacing of 15 kilohertz. So see the number of users it can allocate resources to, a number of users as compared to this. Let's see the difference between the GSMR and LTE. So bandwidth requirements for LTE is 1.4 to 20, and we have already seen that. So modulation is GMSK in GSMR, and QPSK and 16 QAM and 64 QAM in LTE, which is higher bandwidth and higher security. Cell range is 8 km in GSMR, 1 to 30 kilometers, and even more than that if we have a clear line of sight. Cell configuration is a single sector, multi-sector, and LTE in comparison to the single sector. To cover additional areas, data downlink and uplink rate is 100 to 50 Mbps, and LTE, which is 1000 times faster than GSMR. Peak spectral efficiency is 0.33 bps per hertz, which is bits per second per hertz, which is 50 times less than what LTE provides, that is 16.32 bps per hertz. Data transmission is circuit switching in GSMR against packet switching in LTE, and hence faster routing and minimal losses because it's based on IP network. Handover success rate is 99.5% in both the cases, but in LTE it's soft handover and no disconnections and data losses. All IP networks, that is LTE is your IP network. In comparison to these parameters, there are many more parameters that are available in LTE, which are far advanced than GSMR, and that we will use in our implementation. Besides that, there are three features that I want to discuss is carrier aggregation. So you see over here is 20 megahertz. 20 megahertz, 5 chunks of 20 megahertz can be aggregated to make 100 megahertz of spectrum. So dynamic allocation of resources, you have already seen that in the previous diagram. Frequency reuse. So in GSMR, we the different frequencies needs to be used on consecutive towers. So but over here same frequency can be reused in the LTE. There is a comparison of LTE LTR deployment with other countries. So if you see the UK scenario, it's commercial. It has used the frequency and towers of the commercial operator, which is acquired by BT, British Telecom. Hence, the delivery cycle is short, and the security is not so high. High, but not so high, because it has used the reuse the operator's LTE network. So if we talk about the core is dedicated and the geography is large. Core is dedicated in all the cases, but in the Korea and India LTR scenario, the network is dedicated, so it's more secure. And Korean geography is small in comparison to Indian geography. More than 66,000 kilometers of Indian railways stretched from one end to other end in India. So it's also a greenfield project for us. It's a new build, and multiple services that can be used in LTE are ATCS level 2, platform monitor, operational voice, CCTV, PIS, train telemetry, PVIS, public information system. So the red lines that you are seeing is basically the prioritized traffic. So if I have a 10 Mbps of throughput and I want to dedicate 2 Mbps with priority 1 to ETCS, priority 2 to operational voice, then if we have a congestion, then in any scenario priority 1 traffic will get 2 Mbps in any scenario. That is QoS, quality of service, and then operational voice, and then the rest of the 6 Mbps will be distributed among the this sorry different services. So I've already told you that transmission bandwidths up to 100 megahertz are supported. Individual carriers up to 20 megahertz are supported. Carrier aggregation is possible, and hence it's a future proof. So carrier aggregation is basically you are aggregating different subcarriers. So maximum of 5 subcarriers can be aggregated, which if we use 20 megahertz of subcarrier, it will add to 100 megahertz. And by that we'll get the 3 Gbps in the downlink and 1.5 Gbps in the uplink. Channel coding weight is 1/3 turbo coding plus hybrid arc. Arc is automatic repeat request. So 1/3 is the coding rate, so input bit upon the output bit, and turbo coding is basically a forward error correction scheme, which is used by hybrid arc. So automatic repeat request is like the receiver is sending the acknowledgement, negative acknowledgement that I didn't receive the packet, so the sender will send it again, the whole packet. But over here, the certain bits are transmitted, and the packet is reconstructed at the receiver's end. So it's hybrid arc, that's why, and hence saves a lot of bandwidth. Sorry. Data modulation supports QPSK 16 QAM and 64 QAM. So 16 QAM and 64 QAM are very high capacity modulation schemes that is being used in LTE. 8x8 MIMO, 4x4 MIMO in the uplink, and 8x8 in the downlink. Inter-cell interference coordination is supported. So what is inter-cell interference coordination? So it basically mitigates the inter-cell interference at the cell edges. And the cell edge is the farthest end of a cell till it reach. So let me show you what the cell edge is. So this is the cell edge. This point is the cell edge. We have more capacity over here, but the lesser capacity over here due to the coverage. So we are defining the cell edge capacity throughput requirements. So let's move forward. Let's get back to our slide which we were talking about. Yes, no inter-carrier interference, so we have already seen that these are orthogonal, hence no interference. Control plane latency is less than 50 millisecond, user plane is less than 5 millisecond, and hence perfect for our operational voice and ETCS requirements. User plane latency is less than 5 milliseconds because the towers are intelligent and takes decision by their own without contacting the core network. Mobility support for speed up to 500 km per hour and coordinated multi-point transmission and reception. This is also known as COMP. So it's basically improve the signal quality at the cell edge and results in the soft handover. So downlink transmission are coordinated across all the cells within the range so that the signals from the other cell would not interfere to the UE. So it's a very good mechanism. Enhanced support for end-to-end QoS. So I have already explained that in order to prioritize one of the traffic, there should be a support for QoS, and which is there in LTE. LTE is based on OFDM. We have already seen that there is a better in dealing multipath interference. So multipath interference can be taken care by the cyclic redundancy check, which is a feature in the physical layer of the eNode B. So wideband carrier can be transformed into narrowband carriers. This we have already discussed. Intelligent eNode B towers. So when your UE is in or handset is in idle mode, it continuously sends the reports to the tower or eNode B as requested by eNode B. So if you see the RRC layer over here, radio resource control, this layer requests the reports from the UE. So based on that reports, tower knows where what's the location of the UE, what bandwidth it's using, what's the capacity of the UE, and what's the battery power of the UE remaining, everything. So and then takes the decision based on that. And when you move from one tower to another tower, so eNode B doesn't contact with the core network, so it takes decision by its own. So MME is involved, so the packet will go to MME also during the handovers. MME will see what the MME will be. eNode B RAN part is the most complicated technology. Several layers work to get the packet to the air interface, yet no layer is standardized except the air interface. So if you see the user traffic is coming to PDC, PRLC, MAC, and then physical. Several layers are there which is moving the packet from one end to another end, and then it's transmitted through the air interface. So these layers at the eNode B are not yet standardized. Why? So that the network vendor can implement it in its own in its best way, can use the best algorithms it can. But at the UE side is standardized because a lot of manufacturers that are manufactures the user equipment. A number of modulation schemes, coding schemes, we have already seen CRC, cyclic redundancy check, we have already seen security, integrity, etc. Separation of control and user plane traffic. So you can see the user plane traffic is separated over here. Let's go to previous. This user plane, this is your control plane. Control plane is traffic is directly moved from here to here. So if anyone wants to get a deep insight of this technology, he or she can start from this protocol stack diagram of eNode B and start reading to get more details of this particular technology. This is the security part, separation of VLAN, VRF due to IP structure and password tokens and certificates. So if I want to access eNode B or anything, even I can use the certificate to authenticate, or token system is there. There is spoofing, there is a protection to spoofing, sniffing, denial of service attacks, all of that. This is our project scope, which is Jhansi Bhina 155 kilometers, Venagunta Yaragunta 165 kilometers, Vijayanagaram Palasa 145 kilometers, Nagpur Badlaila 175 kilometers. So we are putting the core part in the data centers which are located at Gurgaon's data center and the Secunderabad data center. And we have redundancy planned at each and every part at each and every level, so that there will be no delay or outage of the network. This is the LTE architecture. If you see, this is the train, this is the eNode B, server gateway, PCRF, P gateway, radio blocks, railway block center. This is the wireless UE connecting directly to latching to this. This is MME, HSS. Let's move forward and we will see those things in detail. So this is your onboard unit with an rooftop antenna. This will connect to wirelessly to eNode B, eNode B to RBC. From RBC it gets the signal. okay, whether you want to move, whether the train needs to stop, need to apply emergency braking, or at what speed it needs to run. Let's move more in detail. So this particular node B is connected to our POP through MPLS cloud, and MPLS cloud is connected to our data center. So at data center, this is the whole EPC, Evolved Packet Core. This is known as EPG, Evolved Packet Gateway, which constitute of a server gateway and packet gateway. Let's talk about the MME, which is Mobile Mobility Engine. So all control plane signaling traffic between the UE and EPC will go through it. Tracking of UE in idle modes is done by the MME. UE authentication, bearer management, handover, selection of PNS gateway, support for lawful interception, everything is being done at MME. Then S gateway is the first contact point for end user plane data between eNode B and EPC. Routing incoming and outgoing IP packets to their correct destinations is the functionality of S gateway. So S gateway is logically connected to the other EPC data gateway, which is your P gateway. So this also acts as an anchor point for inter eNode B handover, packet routing and forwarding, event reporting to PCRF. This is home subscriber server, which is a database that contain user related information, and it basically authentication center, which generates authentication and security keys for the authentication purpose. This P gateway, it connects the EPC and the external IP network like internet. In our case, instead of internet, it will be MCPT dispatcher and RBC. So these two functionalities are combined in a single device by the network vendors, and it is known as Evolved Packet Gateway. So it do per user based packet filtering, law interception, IP address allocation, transport level packet marking based on QCI of the associate bearer, the QoS, prioritization of the traffic, policies made on the PCRF, policy control and routing function, and it's being implemented by the P gateway. So MCPT server is already, it will be used for MCPT, making MCPT calls and all the different calls. We are putting this EPG at the field location also, because if we are data center is Gurgaon and train is moving in the Vizianagaram Plaza section, in order to avoid any delay, we are putting this at the field location also. There will be no delay, but in order to be a safer side, we are putting this. In case of 700 MHz spectrum, we are dividing it, the 10 MHz into 55 MHz of spectrum, and at the cell edge we are asking for 2 Mbps downlink, 512 kbps uplink. In 900, since the bandwidth is small, so we are asking for 256 kbps downlink, 128 kbps uplink. Why is that so? From where we have derived this data? This is our requirement. ETCS traffic needs 20 kbps and MCPT at 40 kbps. So based on this, our calculation is made at the cell edge. Let's move on the MCPT services offered. So this was based on release 14 and upgradable till release 16. MCPT user authentication with database and location syncing with dispatcher. So how it is done? This is your MCPT server. This is onboard unit, wireless client, LTE modem connected to the eNode B, but wireless client can directly latch to the eNode B. MPLS cloud, Evolved Packet Core at data center, and then MCPT server. So what does that mean? This user authentication with database and location syncing with dispatcher. So let's move a little bit forward and see. This is the dispatcher server, also connected to the Evolved Packet Core at DC. There will be dispatcher terminal client and console for section controller connected to the MPLS network. So when the driver comes in the cab and authenticates, there will be a database syncing with the dispatcher, so that the location and the functional location of the trains can be sent to the dispatcher, and this console, section controller and station master can make calls based on the locations and can view the real-time location of each and train moving in its own section or a station, and make calls based on functional addressing schemes or location-based addressing. So let's move back and let's see what all features it can provide. MCPDT emergency call. So there is a button also. If you can push the button, there will be emergency call generated and it will be routed to the nearest station master or the section controller. Group calls, private calls, messages, integration with dispatcher for location and functional based addressing, call logging and recording, emergency and video calling not in a tender scope. So in the MCPDT there is an option from release 15 MCX services which is known as. So driver can make the video calls, record it and send it to the section controller or station master as well, but it's not in our scope. Functional based addressing and location based addressing. So based on the train number, the section controller or the station master can give a call to a cab driver. Location, based on location it can call. This is the architecture we have already seen. Now how mission critical push to talk is different from operator's voice service. Predefined KPIs to be met mandatorily for mission critical services. Sorry. So key performance indices, these are already defined for mission critical services and these are to be strictly adhered with. Strict priority QoS services to be followed for preemption of services during congestion. QoS services is basically the prioritization of certain services during emergency or congestion that is already taken care of in the LTE part. No delays tolerated in mission critical services. Full redundant architecture needs to be implemented. So hardware redundancy, it's okay to have a hardware redundancy. What if all the hardware fails or the whole hardware fails? There should be a frequency level redundancy as well. So we have planned that redundancy and I will show it to you through animation in my video. Guarantee cell throughput requirements to be met, which we have already defined. Less number of users and devices in comparison to operators network and hence we can use more services. Dispatcher server system. It will provide the control room capabilities like the ATC to manage and view the train movements through geographic information system and MCPDT calls. So if you see over here, you can see the this red spot. This is a section controller look. These red lines are the trains moving in a particular section and over here you can see the train numbers. So the section controller can have a real-time view of all the trains. So he doesn't need to give a call to a station master and ask for the location of a train. And when we see the comparison of the dispatcher console and terminal client, we will see how many functionalities section controller will have if we deploy this dispatcher system in the railways environment. Call routed to the correct station master or section controller through dispatcher units. So call can be routed based on requirement, location based or functional based. Dispatcher console and terminal will also have the MCPDT hardware to make the calls using all the functionalities. So this particular PC that you see will also have this hardware to make calls, MCPDT calls. It will provide the functionality of functional based addressing in such a way that the dispatcher can call the train by train number, driver ID, locomotive number. These are all the options available to the dispatcher of terminal client and the dispatcher console to both. So let's move forward and see the difference between the dispatcher console and terminal. So dispatcher console is at the section controller side and dispatcher terminal client will be station master sides. Section controller, as we have seen in the slide, that it will have the whole overview of the section and access to all the responsibilities for that section. But station master will have the view of its area of jurisdiction. Moreover, if we want to patch the calls existing IP network, VoIP network to the MCPDT, then it can be done at the dispatcher console only. Cannot be done at dispatcher terminal client along the station master side. So dispatcher console, which is at the section controller side, will be the overall in charge of setting call priorities, emergency calls, and can even override the station master responsibilities and priorities. But the admin access of the section of the station master is restricted to his area of responsibilities. Good part is both of them can make location based addressing calls based on functional and location based addressing. We have already seen the slide. So what are the different components in Node B? So there are antennas, RRU, baseband. Baseband has a software, whether it's FDD or TDD. It pushes the frequency to the RRU. RRU has a power amplifier which sends the signal to antenna, antenna transmits the signal to the different areas that is meant to receive the signal. So these are the different components. The dotted line that you see is the control plane traffic, and the dark lines are the user plane traffic. So you can see this. We have already discussed different components in brief in the previous slides in the network connectivity architecture. So let's move forward. So 10 megahertz of frequency spectrum is already, I have told you that, divided into two chunks of frequency of 5 subcarriers. So let's suppose if we have 701 to 710 of 10 megahertz spectrum, then we have divided into 701 to 705 F1 and 706 to 710 in F2. Since I have already told you that there is no interference between the subcarriers, so we can do the 100% overlap over here. How it will benefit to us? So let's see, this is a normal scenario, train will move. But what if we have one E node be down? We have this functionality, this overlap. Our functionality will not stop because of 100% overlap, and our train will move flawlessly without any interruption. So let's move and say, what if we have only 5 megahertz of spectrum, that is 701 to 705. Now the frequency is same, so there will be interference. Subcarrier is same, so we cannot have more than 30 or 40% overlap. In this scenario, in normal case, train will run flawlessly, there is no issue. But what if the E node B goes down? This particular area will be a black spot. This black spot needs to be dealt with, otherwise the train will stop over here, and we don't want that. So let's see what's the solution for this. So as soon as the tower goes down, and hence the interference and the SINR ratio, that means signal to noise ratio. So as soon as it goes down, there will be automatic increase in overlap due to decreased interference and SINR, and our train remain moving flawlessly without any interruption. So how it will impact Indian Railways? It will leapfrog and build autonomous train. So there will be improvement in the line capacity by 226%. Just 226%. Improve the train operations, emergency response, safety, efficiency, and it will increase the revenue also. The Indian Railways. IoTification. This IoTification, since NB-IoT is standardized and it can use LTE as a technology, communication technology, so we can use different IoT sensors, IoT enabled assets for asset management, predictive maintenance, surveillance, wayside monitoring. We can use that using this technology. Indian Railways for the first time will create intellectual property rights. That means Indian Railways, if implement this ETCS level 2 or LTE, will be first globally and can provide consultation globally and will have the market globally and transform a consumer to a creator of technology, and this will be helpful in realizing the Make in India vision. These are different use cases, passenger surveillance. So there are two ways in which we implement passenger surveillance. One is if a train is reaching to a station, the data can be offloaded, and the second way is the continuous stream of data is transmitted. So in LTE, there can be a continuous stream of data that can be transmitted from the coaches to the controller, and it can be prioritized and it can be routed based on the which control center it should go to. So IoT based services which also include point C, remote health monitoring. There are different field engineers that used to visit and check the different parameters of axle counters, track circles, temperature machines, point machines. So they do not need to go if we use IoT sensors. So IoT will trigger the event as soon as they find some problem, and then the field engineer can go and check, and there will be very easy. It will provide the easiest way to manage the assets and to rectify the problems without disruption in the services. Asset management, smart transport. So we can put the sensor inside the locomotive which is carrying the petroleum. If the top of the container, top of the container is open. If sunlight comes in, it can detect, trigger event. If train comes to a halt, it can trigger an event and send it to the control location. Telemetry services, wayside monitoring, predictive maintenance, Wi-Fi offload, Wi-Fi on trains. These are all the use cases that we can implement using this technology. Sorry, last but not the least, so this technology can also be used for PPDR activities like police, hospitals, transportation services, ambulance, fire services. So these are not linked. So if a policeman is at a disaster location and wants to call a nearby hospital, he doesn't have a number, he can't make a call. He have to call to a certain location, then they will give the number, or they will give a call to the particular hospital. But if we implement this technology in PPDR, if there is a device which we are providing to the Indian Railways, policeman can press a simple button, emergency button, and the call will be routed to the nearest hospital. Hospital can communicate by connecting that particular the transport mechanism which is nearest to that location in a fractions of second. So this technology can really change the whole scenario that we are living in, and make disaster recovery better than any era we have been. So that's all, and thank you for bearing with me, and I will upload more videos on this with more details on the LTE technology. Thank you very much.